Okay, so look up here. If let's say I have this border say I have this border between water and air, and I'm just going to draw the normal.
How much space do we need?
Pretty good amount.
I have one page. Do you need our straight edge?
I'm using my straight edge.
Yep, extra straight edge.
It's extra straight edge.
Straight edge. Straight edge.
Here's some straight edges. There's more back in the plastic bins than are out.
Dr. Steve, what's the thing on the right side?
Air. All right. What's going to happen to that light ray as it comes in? Okay, which direction?
Towards the medium. Towards the medium, because the right wheel hit first.
Okay, the right wheel will hit first, and when that right wheel hits, will it speed up or slow down?
Speed up.
Speed up. So it's going to bend upward. It's going to bend away from the normal, right?
Doesn't matter what you hold, it comes up.
Yes, but we're not worried about it. Now, remember you learned in the law of reflection, when a wave reflects, the incident angle is going to be equal to the reflected angle. In this case, when we have refraction, there is a relationship between the two angles that this year you're not going to have to learn. So don't worry about any math I do right now. Just get concepts. But I'm showing you the math as background for those of you going on, and also to explain where I'm getting what I'm talking about. Right? So, in this case, the angle coming in is again the incident angle. The angle going out is the refracted angle. We have this notion of what we call an index of refraction, and again, you don't have to know that this time around. But the index of refraction just basically tells how fast light travels in that material. So in this case, which end is larger? Well, I'm sorry, don't even worry about that. Because the higher end, the slower the light goes. So, but here's the deal. We can show, and again, you'll do this next year if you go on, but this is called Snell's law.
Snail?
Snell's.
Oh.
Yeah, not snails, not smells.
So you need to know it's Snell's law.
Again, anything math-based today, I'm just showing you for background. I'll make it very clear what you do need to know, yes. All right? But I show you this to make the point that as the incident angle increases, what happens to the refracted angle? It increases also. So, for example, if I have another angle here, with this incident angle, the refracted angle is going to be even larger. Can you then see that there's going to be an angle, which this green arrow we're going to call theta sub c. You'll see why in a second. There's going to be a point to where the refracted angle becomes what? 90 degrees, right. It's going to do this. Right, to where the refracted angle is 90 degrees. When that happens, how much of that light makes it into the air? None. That's called total internal reflection. And yes, it's a concept, and I slowed down as I was writing it, so yes, this would be something you do need to know. There's an angle that when we get large enough, none of the light goes through, it all reflects inside.
And that angle is...
That angle is called the critical angle.
Whoa.
That's why the little c.
So the critical angle is...
The angle that once large enough makes no way.
Right, no angles, I mean, no light refracts, it all reflects. So we don't go from the water to the air any longer. Yes,
So you made it go like this and go straight up.
right.
But then isn't there...
Now there'd be another angle, wouldn't there? Right here?
Yeah.
In which case, what would happen?
It would go outside like that.
Good, it's going to follow the,
It goes back into the water?
yes, it's going to reflect. It's going to follow the law of reflection. So the red and blue rays refract, and they go from the water to the air. The blue and orange rays do not make it in the air, and they stay in the water. When that happens, we call it total internal reflection. There's no light passing from one medium to the other. Now,
Are the orange angles identical?
yes, by the law of reflection, this angle here, guys, stop please. This angle here is equal to that angle there, by the law of reflection.
Okay.
Yeah.
What happens when you have light coming in? You have light coming in parallel and then shooting out?
Ah, parallel point again?
Or it comes that way and then goes that way?
No, because if it's this way, it'll just keep going straight.
Okay.
Yes.
Where is the, so I think probably was also but the angle for the orange is equal to what part of the upper?
Well, by the law of reflection, this incident angle
Yeah.
equals that reflected angle.
Okay. Thank you.
Mm-hmm.
Wait,
Yes.
so... It's kind of hard to... But that angle right below the normal, the red one,
Red one?
is that the same as the one that...
No. That follows Snell's law. This angle relates to that angle by Snell's law, which depends on the ends. And that makes sense, right? Because if it was the same, would it have bent? If this angle was the same as theta r, would the ray have bent? No. It wouldn't have refracted.
Okay,
Yes.
so the green and the orange, do you see like a picture of it when they reflect, or how does that work?
Ah, good question. It depends on how smooth this barrier is as whether it's specular or diffuse, right? Usually it's going to be diffuse. Now, let's talk about, but not always, and we'll talk about that. Let's talk about a practical use of total internal reflection.
I think the recording stopped.
Oh, did it? No, it just doesn't count down on the taskbar. Thanks, Bill. Now, anybody have
BIOS?
BIOS? What is BIOS?
I think green is the rise.
Fiber optics, right? It's Verizon's brand of fiber optic communication system. What that is they have a tube that the light will totally internal reflect in because it's surrounded by this cladding. And they send light signals down that tube. The advantage of the light signals over electrical signals is that there's less noise, and because it doesn't lose much energy because of all the reflection, You only have to boost the signal every 50 or 60 miles as opposed to every couple of miles. So that's what fiber optics is. It's taking light, bouncing it by totally internally reflecting it in a tube in order to send, in this case, digital signals for your TV and internet. Right? There's another maybe less glamorous example of total internal reflection that I want to look at right now.
Like, can you repeat that one more time, please? Like, taking light by totally internally reflecting it in the tube and...
To create energy.
Yeah, to send electrical signals. I mean, not electrical signals, but digital signals. And if you're taking engineering, we'll talk a little bit more detail about what that actually is. But for now, just know the concept. All right, pop quiz.
Fluffy.
Yes, Fluffy 2. There's only two options, A or B. Which of those two positions most commonly and most closely reflects where the location of the light in a swimming pool is? Is it usually closer to A or closer to B?
What do we see in the
No, where is the light actually placed? If I drained all the water out of the pool and measured, would the light be closer to the surface usually or closer to the bottom of the pool usually? Who says A? Where are the A's? Okay, B's.
Wait, no, what was it?
Okay, 3 people voted. That's not
No,
acceptable.
what's the question?
Is the light most likely here, closer to the surface, or here, closer to the bottom of the pool?
Is there neither option?
Like the light in the pool that illuminates the pool. Right? And by the way, it's better to think of examples of like deep pools rather than, if your pool is only like 4 feet deep, then that's not a very good. Alright, where are the A's? Everybody votes.
Hey, buddy.
Where are the B's?
We're both wrong. Everyone's wrong.
Okay. The answer is A.
The lights on the bottom.
The lights are closer to the surface. And it's not... Let's talk about why usually the lights are near the surface. It's not so that the service tech can reach in and change the bulb without, draining the water. That would be stupid, right? Here's why. Let's draw some light rays from B. Oh wait, for those of you who get real anal about the pictures, I'll keep from messing it up too much. There are just some rays of the many rays that leave light when it's at place B. This first one right here, what's going to happen to that ray? Straighter up? Or more away from normal?
More or less normal.
Away from normal, right? So it's going to go like that. It's going to refract away from normal. What about this one? It's going to refract away from normal, right? And then this one? Yeah, it's going to refract way away from normal. We're getting near the point of what? The what angle? Critical angle. When we get to the critical angle, what happens? Reflects internally like that, right? In this case, a great majority of the light ends up where? Outside. Well, some light does.
Oh, never mind.
But a lot of that light reflects off the side of the pool. Now let's take position A and draw some rays. what happens to the first one? It refracts. The second one, how does that compare to this angle over here? It's getting pretty close, but we'll give it refracts. But then what happens to this one?
Goes back down.
Reflects, right? And what happens here?
Reflect.
Reflects. And what happens here? Reflects, right? In this scenario, where does most of the light end up? Inside the pool. A pool at night looks like it's what? It's glowing, right? It's real bright and glowing. Whereas someone standing, or in this case, something standing next to the side of the pool. This is Fluffy 2, right?
You're going to be too
Fluffy 2 smarter than Fluffy 1, don't worry.
Didn't get involved in the mafia.
Yep, bingo. Making bets you couldn't pay off on. Yeah, I put the light source closer to the surface so that a lot of the light reflects internally. So the skirt of the pool doesn't light up much at all, does it?
No.
Where the pool itself is really bright and shiny because of near total internal reflection. Now it's not actually totally internal reflection because some of it escapes right here, but most of it totally internally reflects. It's the same concept. All right? Incidentally, if you look back at this green ray right here, that also causes the surface of the pool to have that kind of glowy look. It looks thick, right?
Wouldn't all those areas where like the lines are be lit up as well? Is that like the bottom light? Or is it the only area that's lit up where the arrow ends?
Good question. Because this light, for example, is going to reflect off the side of the pool and then reflect off the bottom of the pool and eventually make it out, right? So by reflection, some of the light's going to escape. Some of it's going to go like this because light is going out in all different directions.
Right, so
But can you see how if I have it up here, I'm going to have more light internally reflected than I will if it's down at D.
yes.
And that's the point.
And what does that have to do with the critical angle?
Yes. The fact that if I get over the critical angle, the light can't refract anymore. It has to internally reflect. Yes,
Is
sir.
the critical angle the one that's like coming from the light?
Yes, the critical angle is this green angle right here. And it's measured from the normal, and once I get past that, I can't get out. I bounce back in.
Okay, so in the pool, like the critical angle was like the one that was like coming from the light.
Yeah, in the pool, because I have two materials, the critical angle for two materials is always the same, and for water and air, it's like almost 49 degrees or whatever. But I ask myself, at each of these points, like this one right here, was that angle the critical angle or less than the critical angle?
Less.
Less than. So does the light refract or reflect?
Refract.
Refracts. And then I ask, over here, is this angle less than the critical angle or more than the critical angle?
More.
This one was, we called it less than, but it's close, right? And then this one, it's clearly more than. And once we get over that angle, then I reflect. Right?
Can you measure, is that line normal? Is that
Yes.
why you...
Yeah, the
okay.
black lines are all the normal lines.
And then on the other one, we had it like...
Yeah, I'm sorry. Yeah, it's rotated 90 degrees from this picture. Because here the water is on the left, and here the water is on the bottom.
Okay, thank you.
Okay? All right. One more example of total internal reflection, or at least near total internal reflection, is why do they take such care and precision in the way they cut diamonds? Because if you pick the right angles, then the light gets inside and it hits critical angles for several reflections, and it internally reflects several times before finally escaping. What does that cause the diamond to do?
Hey, hello.
Causes it to sparkle, yeah, glitters. It makes it prettier, right? If you don't have those nice clean cuts, you just have a rough diamond, it doesn't sparkle as much. All right?